Okay, so we now finally have the tools in hand to make a much faster Risset beat solution based on the inverse discrete Fourier transform. First, I just want to make a connection between some code that should look fairly familiar given what you did on the second part of homework 1. What you had done there was aggregate a bunch of amplitudes for cosines and sines at different frequencies, and then you took those amplitudes and scaled some waveform over all the samples and added that on to your final signal, right? And you would have done that for both cosines and sine components. And so this should look an awful lot like the last loop that you had in the second part of homework 1. The only difference is you probably had a dictionary there, whereas here we actually have arrays of cosine and sine components. Because we've insisted that the frequencies that are involved go through an integer number of samples, so we can actually index with an integer. So we're in different units here. Okay, but otherwise the structure of this loop and spiritually is very much the same thing, right? And so we're essentially going to redo this with part 2 using these different units, but what we're going to be able to do is use a much faster algorithm to perform this inverse discrete Fourier transform, all right? But first, I'm just going to start off trying to do the same thing that we did in part 2, but with the framework where I'm using cosines and sines to go through integer number of cycles over the interval. So I'm going to change units. Okay, but I start off exactly the same way, where I load in my tune, I load in note numbers, and I load in times. And what I would like to do is just set up everything that I used above when I was doing the inverse discrete Fourier transform. So first I need to know, okay, well, how many samples does the tune that I'm trying to construct go through? And so what I should do is say, okay, well, it's the sample rate, samples per second, times the tune length, which is in units of seconds. That would be the number of samples I need. Let me round that to the nearest integer. Okay, so I've got that. Let me also make space for the sine and cosine coefficients. So the result of the dot product with all the probes that go through integer number of cycles for sines and cosines. Now this is directly analogous to the dictionaries that you would have used, but now we're able to use arrays because again, each frequency goes through an integer number of cycles, and the units here is cycles per interval. So it's the same, but we're using units of cycles per interval, and assuming, so instead of hertz, which was cycles per second. So before we had a dictionary key, which was a floating point number, which was in hertz, cycles per second. Now we're going to have an array index, which is cycles per interval. The only difference that you'll notice so far with what I did above is that these arrays have n samples instead of n over 2 samples. That's for slightly technical reasons. I won't get into it, but we're going to do basically the same thing. Okay. Yeah, so let me just proceed how we did in the Risset assignment. So I'm going to loop through each note. So I'll say, okay, let me get the note number and let me get the time offset. And the first thing I'm going to do is compute the frequency in hertz. So that'd be 440 times 2 to the p over 12 for the equal temperate scale. But this is in hertz. I need to convert this into units of cycles per interval. And so in order to do that, I'm going to, so I'll call this center for my center frequency. Or maybe I'll call it K center to indicate, so K means index into these arrays. So that should be the frequency in hertz times the number of samples over the sample rate. And if you check out the units, that should give you cycles per interval. Okay. So n is the number of samples per interval. This is the number of samples per second. And so if you check the units, that'll give you what you're looking for. Problem though is this is not exactly going to be an integer. So what I'll do is I'll just drop it down to the nearest integer, and you'll never notice this in practice. Okay, this has to be a whole number in this framework, but not a big deal. But now here's the really exciting thing that we can do now that we're in these units. remember, our goal with Risset beats is to create a beat that frequency that happens once over our tune interval, right? So when I was doing this before, I made sure that the frequency right next to me was either up or down by 1 over the duration of the tune, because that would create a frequency that went over 1 cycle over the duration of the tune, right? So the beat frequency is the difference between the two. But here we're already in units of cycles per interval. So if I'm at a frequency of k center cycles per interval, and I go to the frequency k center plus 1, for example, well, the difference is 1 cycle per interval. So now what we're able to express in a very elegant way, we're sort of in the exact right units to express what the nearby frequencies are that are going to create the beat that's at the frequency that we need it to be to happen once in the tune. Okay, we're trying to have each note happen once. We want to make sure that the beat frequency only happens once per interval. And so literally that's just adding or subtracting 1 from the center frequency. And then of course the trick with Risset is to keep doing that. So now add and subtract 2 and add and subtract 3. So what I'll do here is I'll loop through a difference in k. I'll call it dk. But in integers. So I'll say in range, I'll say negative frequency frequency per note over 2 up to frequency, frequency per note over 2 plus 1. Now this is not exactly going to be frequencies per note, but it's roughly right. It'll be equally spaced on both sides. And so now I'll say, okay, so the frequency k that I'm trying to add into this mix is k center plus dk. All right? So again, these units align perfectly with what we're trying to do in Risset, which is really cool. So now we need to do that thing where we accumulate this phase change. We do have to now, at this point, convert back to... Oh, and I should be a bit careful here. Let me not call this S. Let me call this, because I've already used S to refer to the signs here. Let me call this U, or maybe I'll just call it shift. Okay, this is my shift in time. So I do need to convert, in order to get these units right, I do need to convert back to frequency in hertz. So that would be K times, so I'm just inverting this formula here. That would be K times the sample rate over N. So I'm going to accumulate, this is exactly like what you did in the assignment when you had a dictionary. If C was a dictionary here, then this would, and K was the frequency in hertz. This is looking exactly the same, but remember, it's 2 times pi times the frequency times the time shift, right? That's what I'm accumulating into this array. And then I do a very similar thing for the sine component. Just make sure I change this to a sine here. And so now this should look very similar to the first loop that you had setting up your dictionary. The only difference is, instead of a dictionary, we have these arrays of the Fourier coefficients, is how we interpret this. So we're just in different units here, units of cycles per interval. And then we can accumulate things the same way. Nice. Now at this point, I could, just plop in the inverse discrete Fourier transform code. That would actually defeat the purpose of making this faster, because it turns out there's a much faster algorithm called the fast Fourier transform. And I wrote some code ahead of time that I'm just going to plop in here. You don't have to worry about it too much, but I'm just setting up the code, or I'm setting up the format to use the fast Fourier transform, which, for those who've had data structures, this is an O of n log n algorithm, whereas the version we implemented above, the brute force version we implemented, is big O of n squared. All right. So what I'm going to do, let me just see if this runs first, and then I'll explain why this is. You're going to see how much faster it is, and I'll explain. I'll actually do a little arithmetic to validate that. So hopefully I got this. Okay, let's see. So first of all, did you see how fast that ran? let me actually time it. So this is doing the thing where, actually I even upped the sample rate too. Now I'm at sample rate of 44,100 per second. Before it was, I could only do 8,000. I kind of sacrificed a little bit. But this is so fast, I can up my sample rate. So let me go ahead and print out the elapsed time. So in a quarter of a second, I was able to do 500 frequencies per note over 70 seconds at a much larger sample rate. Let's hear, did I get it? There we go. Okay, so that worked. So, the structure of this code is very similar. We're still setting up all these coefficients, some for cosine and some for sines. But we're doing this magic algorithm, which I'm not able to explain right now, but we'll take it as a given, that is able to do this inverse discrete Fourier transform where it sums up the contribution of each cosine and each sine over all the amplitudes. It does it much faster. It doesn't have to go through every sample for every frequency. Exactly. It's able to do this divide and conquer algorithm to do it much faster. So for those who've had data structures, it's sort of analogous to like the version that we did here for the inverse discrete Fourier transform, which is quite similar to the one that you did in part 2 of the homework. This would be like, insertion sort or bubble sort, big O of n squared. Whereas this would be like merge sort, big O of n log n. And so just to, back of the envelope, let's look at the difference. So n is enormous for our tune here, because we got 44,100 times 70 seconds, right? And so let's just look at the ratio. So it's the ratio of n squared over n log n. So that'll give us the factor of speed up. That will be n over log n. Actually, let me choose a base for this. This is log base 2 of n. And, this is up to constants, so this is not absolutely correct, but I just wanted to give you an idea. N squared scales very poorly as n gets large. This is really going to blow up, and n log n is not. So let's just get a back of the envelope estimate of the speed up here. So n over log 2 of n. This is humongous. This is almost 150,000 times faster than it would have been. Now that's, it's not completely fair because it's also going through all the frequencies that are zero, that are never used. So you do a little better with this dictionary because you only go through the frequencies that you actually used. But in the worst case, it actually could be that much faster. And we see it in practice, like a quarter of a second to do a minute of audio is all it took. And so if you want to use Risset beats in compositions that you do moving forward, you should use this code. All right? So here it is. Use it. We didn't have enough to really do it in the first assignment, but now we do. And so I hope you're as excited about this as I am. And let me know if you want to discuss this more or if you have any questions. I'm just going to have one little quick exercise for you to do to make sure that the inverse discrete Fourier transform was clear. All right? See you in class.